do Atmega based coding using this AVR library. Okay. So far, what we have used is so far what we have used till now for programming is the Arduino library or the Arduino framework, right? So we are going a level lower into the programming. Yeah. Hope my screen is visible. So till now, what we are programming is this Arduino-based framework where we just code the setup and loop function, and most of the functions are defined in there. Those are the functions that we see are usually the high-level functions, like digital read, digital write, right? So these are some high-level functions which have been implemented, and also you have analog read and analog write. So to read an analog value, there's many things that need to be done in order to get you that value. So, and similarly for the digital values and other things. For example, we might have seen this PWM pins where we generate use analog write function to create an analog like value using PWM. But how it is actually generating that? Uh, what are the things that are used behind the scenes? So we are going to dive a lower level to see how that is implemented. So before that, I'll introduce you the AVR library. So AVR, so actually this Arduino library is built on top of this AVR library, which is for this 8-bit RISC microcontroller. So the microcontroller that is present in this Arduino chips, so this chip, this an AVR chip. The specific model is Atmega 328P. This is the actual chip that is present in the this 8-bit AVR microcontroller is what is present in this Arduino boards, right? So we are going to dive a little deeper. So we'll be uh, reading the pins as seen from this microcontroller chips. You can see the pin names are like this: PC1, PC2, PD1, PD2. So these names are actually the alternate names that are given in the Arduino docs also. You see this documentation in the sheet. You can see these alternate names, right? PB, PD, and PC values. And this is the Atmega 328P chip. I think that is here, right? And we are going to see directly how it is happening. The PD, PB values are there, right? So PB, PD is basically the port names that are given to it, and what are the different pins that we have. All the things are given here, right? So there are multiple peripherals that are connected to these things, right? The I/O ports, and we have interrupts. How we can create interrupts in a lower level, and there are timers which helps us to create these kind of uh, one for measuring time. We use delay functions, right? So this delay function internally measure a timer times using these timers, and also this PWM output where we generate this PWM output to create varying voltage levels, which is actually not actually varying the voltage level. We just uh, set up this timer so that the amount of time period that this pin is on is higher, and the amount of time this is off, it is lower. So those kind of things we can do with timers, and also the UART and the SPI I2C, all those things you can uh, do using this. For example, this UART is what you call as the serial output, right? So this will have low-level functions that you can the register level details which you can modify to create that things. Okay. Okay. So if you see in this library, this is the library that we will be using to code these things. So what are the things that are present in this library? That mostly it will have all the uh, things, and also the board related info for the specific board. What are the pins and stuff? Uh, 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 so IOM 328P is the IO map header file, which is having the register level details for our particular board. So it has basically defined statements which correspond to these addresses. These are the memory addresses, right? So instead of directly giving the memory addresses, we can use these kind of names to address the port B and stuff. So all sorts of definitions are defined in this file. So if we include this library, we'll be getting access to these things. Uh, these are the names of the register. Because using the names, we need not remember the address for a particular register. We just use the name of the register to uh, use the value. Okay, I'll just put in this. You actually don't need to clone this thing. Usually, if you are using Arduino IDE or WorkMe, it will be included there. So you don't need to uh, clone it. You can just look it in the GitHub itself. So it will be this library will be available in all Arduino platforms because Arduino is kind of built on top of this library, right? And you might need this things you might want to look in. These are the reference manuals for those, and this one. So take a look at these manuals. So, so that's it for that. So we include that thing. Okay. Uh, okay. So now uh, let's see the basic thing. The easiest peripheral to use here is this I/O ports. So I/O ports are the easiest uh, peripherals that we can easily operate. So what can we do with the I/O ports? GPIO ports, reading, writing the values, right, for a particular port. So you can see this reference. So how we can configure the uh, pins. So configuring the pin means setting to the input or output modes. We set different modes, right? So this is setting that. So what are the registers that are needed for setting those? And how do we toggle the values, switching the output? So what are the registers we need to uh, update to change the values or state of the particular pin, right? So first of all, let's see about configuring. So for configuring, we need these three things, right? Uh, DD, which is data direction, and the port pin and the pin number. So that's how we need to configure. So this is about selecting the direction, and this is about whether this is pull up or pull down, as you can see over here, right? These values. These are the okay. So these are the data direction. This is the data direction value, what we are going to set it there, and this is the data port number, like the uh, for the particular port and the particular number. This value, this particular value represents whether it is input or output. So if data direction is zero, this doesn't matter. Data direction is zero means which means it is input. Data direction is one, the DD is one, which means it is output. So if in the input mode, what does this changes? This value, changes whether it is a pull up or no. So that is the difference. That is what this port XN is doing over here. Right? And This is the, what does this do? Sorry. Uh, no. So this PUD is what specify the pull up or pull down. For zero it is this one, and for one it is this one. Okay, that is how it is. Okay. So now let's see how we can see uh, read and write the values. So first we'll start with writing values because that is the easiest one. Okay. Uh, so go to the register description. So in each section you will find this register description part where you will be seeing all the registers associated with that. And so what we saw here is the name of the particular bit. So you can see, right, this is the DDXN is basically the data direction for the particular port and the particular pin. That is what DDXN and port XN short form means. So all these are the name of these are the name of so if I say DDP7, it is the name of a particular bit in a particular resistor. Okay, and if I say DDRP, which is the register holding all these bits, the DD bits, right? So port P is the register holding all the port bits. So this is a kind of notation that people use to mention the combination of certain bits. So what does this mean is DDXN and port XN 0 1, which means DDXN is 0 and this bit is 1. That's what this kind of notation means. So you should get familiar with this notation where they name a bit and also there is a name for registers. So we should be understanding what are the registers that are present and what are the bits that are present. So here we seen that this one, while setting this thing, so there is this. These are the bits. This is the bits, and this is also bits. So these bits are there, and also the corresponding mm, registers also there. So this PUD bit is present in MCUCR register. This is the name of the register. So usually the register name will be short forms like this, right? Okay. So now let's see how we can write a value to a particular bit. So to write a value to a particular bit, what are the registers we need to modify? First, we have to set up this one output DDXN. So let's choose a pin first. So here, assume I am choosing this D13, which is EB5. So I'll go here. So I have a main and just a main, no loops. I will be just setting the modes and turning on the light. So I'll be connecting LED in 13. Uh, in this we should include it like this. this is how we need a IO thing. So here, this is not what we want to include. So we need from this AVR, we need this IO mapping, which is what is it? We need this IO.h, where our IO mapping is also this header files. This all the header files is included here. Based on the device's name, the particular IO mapping will be included. So we need to include this particular IO mapping for us. And here what we have to include is, so first we have to set the data direction. So we choose the B5, BB5. So data direction for so this is the data direction register, right? This RB. This DDRB is the register for the port B, right? So this is the register. We have to set the value. So to set a particular bit, we use and this R equal to, which is like Ring with the existing value, and we R with the mask. So what is the mask we need? So if you see here, this is the DD, right? So this is the DD particular value. So this particular bit, which is basically numbered from this, right? So if you want to create a mask that covers this certain bits of this DDRB register, what should we use? You can use either. So basically, these are just the numbers, right? This 1 to 8. So you can either use this particular DD6, or also you can use uh, this. Okay, we'll use this itself for now. DD B 5 is what we need, right? So we'll do this. So now the data direction bit is set to output. So this is basically setting in mode. In mode 13 out. So that's what that line means. So we are setting that particular value to output. And then what we need to set up, setting this pin value. We need to set this 4xn bit, which is present in this one, port V register. So what is that? We need to set it for output. For output, there is low and high values are there, right? So 0 means low, 1 means high, right? We need to set this port B5 value. For that port B5, we have to set up the value. So port B, this is a register. We have to set the nth bit. B5. This is the value that we have to set, which is basically right 13 I. This is what that line means. So let's see how this works. Set up this to 1 and this to 1. It's connected to the pin, which is BB5. Okay, just a minute. Check if we have missed anything. Uh, yeah, there seems to be a mistake here. So one thing we have missed here. So here these values, as we have seen in this library, these are the numbers, right? Uh, which means these are numbers from 1, 2, 3, 4, 5. But what we are actually setting here is the uh, we are creating a bit mask, right? So usually when we create a bit mask, we do this. We shift 1 to that many number of places to create the fourth bit as 1. This is how we create a bit mask, right? If I want to create a bit mask with 4 and 5 fifth position as 1, I'll OR it with this particular bit mask. So these are basically numbers, right? So what I have to do is I have to do 1 shifted by these many values. Okay, so this you can. Now you can see that LED is blinking, right? So to make things uniform, so there this Arduino AVR library also provides us with another macro called BV. So BV of 4, which means basically 4. So it translates to that, so that we don't need to use this left shift operator. What is BV? It's basically bit value. So this is help. This will help us creating masks. And also, as I said, all these are basically numbers. So either it is the data register or port B. It doesn't matter what the thing is. It's basically 5, right? So there are multiple ways you can do. You can either use PV of 5 directly, not a problem. And there is also this P and some number. Basically, this all means the particular number, right? You can see everything is defined as 5 only. That particular number. Those are just mappings in there. So to create a bit mask, you don't need to use this whole thing. You can just use the number itself if you want. So we can just go with the PV of 5, and here also PV of 5. That would make sense, right? So let's run this. Please get the same. Now let's see how we can do. Uh, I am going to connect uh, LED bar graph. And if I am connecting, say, this is the negative one, right? We'll connect it to ground, and this one connected IN1, generally 8. Okay, so this one. So 6, 5, 4, 3, 1, 0. This should be fine, I guess. And connect these also. Eight, 7, 6, 5, 1. We also have 0. You know it will be 7, 6, 5, 6, 5, 1, 0. Okay, that's good. We do have something good. So now we have did the connections, right? Let's say I want to turn on all these LEDs. What should we do? Anyone? So we need to see what are those pins first. So this is basically D0 to D7. This is all the things there. And here, this is D0 to D7 and P0 to P5. No, we are having just this two more, right? PV0 and 1. Correct? So we need, in the B port, we need 0 and 1. So 0, 1 will take that, and then here it will be related to high. What about the D port? We need all the values, right? Uh, how we can get all the values? We can do one thing. So what will be one shift 9? It will be, sorry, 158 is fine. 158 will be 1 and 8 zeros. So let's take one shift 2. If you minus 1 from this, what it will become? 1 1, right? In binary. So basically this is 4, and when you minus 1, it will become 3, right? And that will happen. This is 8, and from 8, if you minus 1, it will become 7, right? And in a similar manner, if we do this, instead of creating BV0 to BV all the way to the end, you can create this. You can even call this calling that all on. We'll set everything to high. Okay. Speed. Okay. Now let's listen this, see how it works. Okay. Something connections are missing here. Wi-Fi. Okay, 7, 9, 8, 7, 6, 5, 4, 3, 2. So as you can see, we are basically switching on all the LEDs just with two statements. We don't need to write everything or a loop. No, nothing is needed. Just a bit mask and bit setting thing. So as you might want to turn off certain uh, from the port D, I could also do. How do you reset? How do you reset the value? You AND with inverse of that, right? So if I want to turn off VV of 0 and 1, which is D0 and D1, which is basically these two things, right? I could AND with the inverse of this. Now you can see those two will be oops, what is it? Uh, it's only so this one. Always confused between this R and that. Now you can see this. These two are off. So this is the bitwise not operator. Okay, and these two are off because we have turned it off. So it's initially turned on everything, and now we are turning off this two, right? So you can do in that manner. Okay. So now one more thing that we can use from here is the delay function. we are here. There's a delay dot fetch. There we have util delay, which is being included. Where is it? Utils. Delay. What's that? Yeah, here you can find this delay dot h. So this is what we'll include to get this. There are two functions over here: delay us and delay ms. Uh, so delay millisecond and delay microsecond. Those are the two functions that we have. We can use this function to create a delay similar to how we use the delay function there. Uh, so we'll add delay to create a blinking program, right? Can create a blinking program. So this is all on. So we'll use a loop over here. So we set the pin modes. These are the pin mode cards. So that will be doing only once. And then we can use a while true loop, which is basically looping forever. And there we'll add this digital rates. So this is turning on all the LEDs. And we'll include that also. We are interest delay dot h. Right there we'll add delay ms 1 second. Oh, sorry, millisecond. 1 second is not fine. 1000 millisecond. And we have to turn off, right? So we have to AND with the inverse of this. This is basically all on and all off, all zeros, or we can actually use which is all zeros, right? You can even do that. And okay. Ending with 0 means all 0 and everything will be 0 there also. So that is basically all off in our case. Or you can do either bitwise invert the all on to get back the 0. And both will work. See for our blinking programs. See till like this. Till right. See just tilted dot h. Yeah. You can see we have created a blinking program with 10 LEDs, but just two statements and a for the while loop. We don't use any for loop for doing this. Inside that, usually if you are doing this by Arduino, you have to do more for loop and digital rate statement, right? So this might not be very reader or developer friendly, but this is a most efficient way with which you could directly access the register and change the register values to uh, do the things. So this is a very low level code in that sense. So any doubts till now? Anyone?
Sir, can you explain once again the DDR and port? Like, what exactly do they do?
So those are the registers. So uh, this microcontrollers, they work by uh, changing the values of the register. So if you want to set something, everything, you have to write a certain value to a particular register, and you can read a value from a particular register, right? These are the names of the registers. Okay. So port DDRB is the data direction register for the port B. So all these details about the registers are given in this part. What is this DDRB? It is a port B data direction register, right? So what is port B? This what is this? Data register.
Okay, so the port B are the different pins on the digital side of the Arduino.
Yeah, you can see there are different ports, right? There is this B port and the D port, and this analog are the C ports that you have here.
Okay, so for we use port C for writing it and data register for defining it. Like, what does it do?
Data direction sets up whether it is input or output mode. So if data direction is one, it is
Yeah.
output.
Okay.
Similarly, the data register, which we call the port B register, right? This is the actual data, which means it says if you write 1 here, it will be on, high. If you write 0 here, the state will be low. What is the actual value in that particular pin? So we said digital write high, right? So what the digital write high will do is that line will basically change this particular value.
Okay, so digital pin 7 will be turned
Yeah.
on the
So here you can
Arduino.
see, right? This function, what it internally does is changing one of these values.
Okay.
And similarly, the digital write. This is what digital write internally does to turn on the value.
Okay, and this BV0 and BV1. So these two, did you like logical or is it or a conditional or like
Logical.
it's
Conditional, it
logical?
will be two double pipes, right? For
Okay,
conditional,
yeah, yeah.
bitwise. This is bitwise. These all are bitwise operations. We are manipulating bits.
And what is D at the end, like port D and DDRD?
The
I
name of
understand.
there are many ports, right? So you can see here. So port B has its own set of registers. Ports D has its own set of registers. Here there are multiple ports, right? These pins are connected to the port D. These pins are connected to
Okay,
port B.
got it, got it. Thank you.
Anything else? Anyone?
Just to confirm, like, which week is this content from?
So this is not actually covered in the theoretical contents. You might
Or just
you might have in the initial weeks you might have seen what are the different types of programming, right? The bare metal coding, uh, the Arduino coding, STM Hall based coding. So there are different types of coding. This is the part which is corresponding to the programming aspect of this course.
okay,
So when you actually code, the same thing you do in different ways, right? You will be having in week 7 you will be having exercises which has this kind of programming assessments where you need to use Arduino's this kind of Atmega programming. We'll be using Arduino timers. So when doing that, we need this Atmega things because in Arduino library you cannot directly access the timers and manipulate them.
okay. So we won't get this increase one.
No.
Okay,
This you will be getting in the week 7. So I just introduce you so that you can uh, just practice this also. Okay. Yeah. So this is what is below the Arduino layer of code that you write. So whatever you write in the setup function will be called around this place, and the loop function will be called around this place. So that's how generally this works. This is just like a C code. Every Arduino code that you write, it finally gets translated into something like this. Okay. So now we have seen how this digital write works. Let's see how digital read works. Right? Let's add a push button. So we have set up a push button. Now, what are the things that we need to do for this push button? This push button is in which pin? BV. This is a port B 5. 0, 1, 2, 3, 4, 5. This is sorry, port B 0, right? 0 to 5. It's the 5. So, what we have to set there? We have to set. So here it is set to setting to 1. We can also set a particular reset. We want to set it to 0, right? The direction to 0. So I am doing it explicitly. I'm explicitly setting to out. Sorry, input, which is for pin 30. Yeah, right. So, oops. Now basically, I am turning off that particular fifth bit, which sets the mode to 0. Right. So let's see on how we can read this value from this register. Right. To read the pin value, so first we have to set it to this 1, read it to 0 that we have set, and then what we have to do, what can we read through the pin X register bit. So we need to use the pin X register bit to read the particular value. Okay, and and uh, we have to set this MC or this MCCUR. We have to set whether it is pull up or pull down, right? So that one we have here. We have to set this one. So to set whether it is a uh, when this bit is one, pull-ups of the IO ports are uh, okay. When this is one, this is pull-up disabled register. So we need the pull-up, so we don't have to set this one. This is the pull-up disabled register, right? So this is like globally disabling all the pull-ups. So for us, we need to get the data from here and oops, to read the input. Uh, so we have to set this one to high. So this is basically setting the value to high. Oh, sorry, this one. This one. Uh, ha. This one is if we enable this, there will be no pull up. So we are going to disable this, and we will be uh, So we'll set the data direction to this one, and this will be, we'll be setting to 1, the port value. Just the port value sets the uh, voltage to high. So basically turning it in the pull-up mode, right? So this is what we want. So we'll be setting this to 0 and this to 1 for that. So this is 0 that we have set up, and the port value will be setting to port B. We'll be setting to high, right? You have to set it to high. So we set it to high or with this value. So now these two lines are required for this pull-up mode. These two lines are basically setting up in the input pull-up. Two lines. What this line is doing is setting pin modes for all the other outputs. These are like inputs. Okay. So to read the value, what we will be using? We will be using the pin value, the pin XN bit, which is this one. There is that pin B5. This one, pin B5 is where we get the input value from, whether that is high or low. Right. So, here. So what we'll do is, instead of doing this one, the delay based thing, what we'll do is we'll do a if statement. If pin B5, so we want to select that particular bit, right? So pin B is the register. So if you want to get that particular bit's value, what will you do? Anyone? So basically you want to read the nth bit of a particular register. So how will you get the nth bit of the particular register?
XOR? Are we
No,
doing XOR?
no. So let's see. Let's say I have this. Uh, okay, 0, 1, 2, 3, 4. I want to check whether this fourth bit is 0 or 1. So the way to do this is, what you can do is, you shift this whole number to right side by that many number of positions that you want. So here I want to shift it by 4. 0, 1, 2, 3, 4. Right? If I right shift this to 4, what will happen? What will be the result? 1001. Right? This number will come to the end. This particular bit that we want will come to the end. Right? Is that correct? If you want the end bit, you can do it. And now we just AND it with 1. Just 1. Then what will happen? All the other things will be made 0. Okay. So if this particular bit is 1, we will get 1. If this particular bit is not 1, we will get 0. Right? Because we are making all other bits 0 by ANDing it with the 1 and all the bits zeros. So to check a particular bit, we get this register, right shift it to the number of bit that we want. So we want to check the fifth bit, and then AND it with 0x01, right? Which is basically 1 at the end and remaining all zeros. So this will check whether that particular value is true or false. So this is what I'm checking is, I'm checking digital read of the pin number would be 13, right? digital read. This is what I am basically doing with this statement. If you are not very comfortable with bit manipulation, bit reading, this whole code will look like some kind of uh, what do you say, archaic uh, things, something without any meaning. But if you look into the bit manipulation concepts, if you are comfortable with that, you will be able to read this as how it goes. So now if this is one, what we'll do, this is one, we'll do high, setting it. Else we'll do low. Okay. So basically we are checking the bit value of that particular thing and then doing. Let's see. So if I press the, so by default, now this is in the pull-up mode, right? So by default it should be one and all the lights should blink. Let's see how it works. We haven't made any mistake. It should work. Everything is there, and when I click it, there seems to be some noisy signals coming from the serial. Just ignore that. So this is what we wanted, right? Now it is in the pull-up state, and everything is on because high. Now when I press, it goes to low, and everything is on, right? If you want the opposite effect, if you want to take account for the pull-up effect, what we usually do, we take the negative of the thing, right? So we can negate this whole thing. You can, I think you can do a logical negation also, because 0 1, that will also work, I guess. So by default it would be 0, and when we press this it should be 1. I think this output is because of we are using this TX and RX pins, right? That's why this seems to be coming, I guess, because those two pins are serial pins. So the values that are going into that pins might come over here. So now we have seen how we can set up input and output with the. So to summarize this, what are the pins that we need for setting up outputs, the data direction, and the port pins, right? What are the registers that we need for the reading the input? We need data direction, port pins. So port pins for inputs set up the pull up or pull down, whether it is to be need to be high or low by default. And then the uh, pin register gives us the use to read the value from the pin. So using the pin register, we can read the particular value from the. Assume if you want to toggle a particular uh, thing. So what we do whenever mm, this is fine, I guess. Toggling. So we did the delay part, right? We did delay by on and off delay we used, right? Instead of on and off delays, we do a toggle thing, using toggle instead of using on and off like this. We can do just one thing. We can do a toggle. So to do a toggle, we XR with the uh, mask. This is the mask. Instead of Ring, we do XR. So for toggling, this is basically toggling. So they just don't have to repeat on and high and low again and again. So this basically means pin the toggle, right? That's what this means. So by default, whenever we restart, it's going to be toggling 1 second, right? You can see the whole thing is toggling. And then we can also make that whenever I press the button, this will keep on running. Otherwise, it won't keep on running. So in that scenario, it would be like this. When I hold the button, this will keep happening. This will happen. If I release the button, this won't happen. Uh, Basically, that I think doesn't need anything. Whatever state it was there, it will be in the same state. It will continue to be in state if I release the button. Otherwise, it will keep on changing the state. So now let's see. Now it is in 0. It will always remain 0. I hold. Now it is 1, 0, 1. I leave, and it will stay as 1 forever. And when I then press, it goes to 0, 1, 0, 1. In 0, if I leave it, it will be staying 0 for forever. So basically, I can hold to change the states and release to keep the states fixed. So even with this kind of register-based programming, you can implement very different lots of logics in this. So you get the idea how we are doing this. You can create your own macros also for doing this kind of stuff. So what is this basically? Huh? So you can define something like this. Read uh, read pin. You can call it like that, and this will take the uh, port name and the pin and what it will return. Pin this is concatenation, right? This we just need this pin name. Use brackets. Let's see. I'm not sure. This is the system's name for name. Pin and 0x. So basically, now this whole thing, this read pin will convert to this kind of expression. So instead of using this like this, we can do what we can do is read pin b. Right. So that makes it more readable, right? So this is also one thing that you can try. You can create your own macros for this bit manipulation operations like this. I think we can also make it a little smaller. Like we could attach this pin suffix into here. I guess it should be. Let's see. It is double slash like that. Yeah, seems like this only. Again, and let's try this out. concatenation name, and here we can just do P. Read pin P5, so it will be port to be pin 5. Let's see how this is working. Definition operator. I think it needs to be string for that. So, this is string. Pass it as a string. Oops. Should this be a string? Then I think that won't work. Let's go with this self. This is fine. Okay, any doubts on the reading part? So what are the registers that we have worked with? Anyone? So this one, there will be revision sessions next week. So there we'll discuss about quiz one related topics. So what are the registers that we have seen? We have seen the DDR registers, pin registers, and port registers, which we use to write and read data from the GPIO pins. Okay, is that clear? Everyone? So is anyone willing to demonstrate a task that I give? I'll be guiding you and you will be doing it in your system. That way it will be a practice and recalling what we have learned. Anyone is willing to do that? I'll give a task with this one and you will be doing it. I'll be guiding you to do that, but in your system. Anyone? It's no one willing. Okay. Then shall we see about interrupts? What we can do about these interrupts, external interrupts and stuff? So IO port is the easiest one that we have seen. So then we will be seeing about external interrupts. External interrupts are like what? The pin-based interrupts. There are lots of different other interrupts are also there. Timer-based interrupts. In timer itself, there are different interrupts that you can create. Comparison-based interrupts, overflow-based timer interrupts, and capture events. Many things that you can create. And this one is the pin change interrupt. This external interrupt is there, right? And the pin change interrupt are like whenever the value of the pin changes, you can trigger an interrupt. You can see, right? In external interrupts, you have this pin change interrupts things. So what are the different uh, registers that we have to set up? So there is this external interrupt control register A. Control registers are like setting of the settings. You can see we set usually the state like falling, rising, and stuff, right? So that one we set using this configuration registers. So this is the falling one, and this is the rising one. So there are these 4 bits, right? So there are 2 interrupts that we can set up. Okay, so you cannot attach more than 2 external interrupts. So that's what this says. That's where we have provision for only 2 interrupts setup, and there we'll be setting whether it is a. So this is like always low. The so we saw interrupts here, right? The language reference. The language reference for interrupts. We have seen the different modes, right? Uh, this one, attach interrupt functions. What are the different modes we have? Low, change, rising, fall. And the same thing you can see here. This is basically low whenever the state is low. This is any change, which is basically rising and falling. Change, falling and rising. These 4 modes are there. Here we just use this kind of name to specify that. But here we have to set up the pin. So there are 2 interrupts that we can set up. So 1 is for the interrupt 1, 1 0 is for the thing. So these bits are called as interrupt sense control bits. These are bits, not registers. The register is EICRA, external interrupt control register A, right? So these are the registers, and these are the bit names, bits in that register. So if we are going to control setting up that particular value, requires us to set these bits in this particular register. And this is the mask register. So enabling, so this mask set helps us enabling the particular register. If we set this value to 1, then which means this we are enabling this particular interrupt, and this one is for enabling this particular interrupt, right? And this is the flag register. So what this flag register is, we don't need to manually do this. Basically, if this is 1, then it will trigger an interrupt. So whenever we change this value, it will change this value to 1, so that the system knows that there is still an interrupt trigger that is pending. So based on this value, this will be automatically changed when we give an external interrupt. So based on this value, the thing will be changed. The interrupt will be triggered. And this is the pin change interrupt controller register. Like the change things. So there are 2 ways that we can: external interrupt enabling, right, and then pin change interrupt. So pin change is like so these external interrupts are what we do here, like setting up all those things. Pin change interrupts are like whenever the value of the pin changes, then only that comes. So this pin change interrupts, we cannot set up this rising or falling or those kind of modes. So basically, you can set these external interrupts, two pins, which we can set up that particular mode. And this one is like pin change interrupts. This only will get triggered whenever the uh, value is changing. This one, this external interrupts will be triggered by these pins or these pins. So will trigger as configured. And okay, so before going into the pin change interrupts, we'll first see how we can set up the uh, just this sectional interrupt, right? So let's take a code and see how we can translate that into this one. So let's take this code, right? Let's see how we can translate this whole thing into that. For now, I'll just comment this. And also, we should be noting that what are the pins that are enabled for interrupts. Only this in R3, interrupt pin number 2 and 3 are available for these kind of interrupts. Not all the digital pin has that values. So we should be using either this or this only. Okay, so this is for mode and this is for mask. So where we'll be setting the pin number. You can see this, right? Int 0, the these are the pins, this PC int values, and these are the int values. So this int 0 and int 1 are connected to this 2 and 3, as we saw here, right? 2 and 3. So to enable that external interrupt in pin 2, we'll be modifying this int 0 and int 1. And for int 0, this we should be controlling this ones, and int 1 we'll be controlling this ones. So attaching that pin to that particular thing. So this line, digital pin to interrupt and this attach interrupts is basically translating these values. So pin to interrupt means it will control change this pin number to this particular interrupt number, which we can call int 0 over here. Int 0, it will convert this number to int 0. So that's basically converting that interrupt. Right. So let's see how we can add this. Assume so I think we need to modify the circuit for that. Okay, let's have this here. Say this. This one. Oh, interrupts are not explained previously. Okay, interrupts means uh, those are small functions. For example, if we have this, right? So what this basically says is we are attaching an external interrupt. So interrupts can be many things. So some event that causes some, there are different events that can occur. So certain events cause some function to run out of this main program. So usually whenever this we when we run the code, this loop will be running forever. So basically main code will be running, right? The main function. During that running that main function, if certain event happens, there is some other function that will run by, will pass the main and will run some other function. We complete that and then come back to the main and continue. So those are like interrupts. Certain events that trigger some external function to run during the main execution. So the main execution will pass and it goes and does that small thing that we have to do and then come back and continues. For example, what they are doing is they are using an external interrupt to change the state of a particular pin, right? So here the state variable is the global variable. This loop will be writing state here. So what this interrupt is doing, whenever this interrupt happens, this function will run. By default, this loop will be running forever. Whenever we press that button, according to this definition, what will happen is, whenever the value of the button changes, whether it goes from high to low or low to high, what will happen? The state will change. So when you hold the button, so if you run this code, let me run this code. So when you run this code, whenever you press the button, it will be on, and whenever you release the button, it will be off. It will be like that. So let's create a new project. Let me paste this one. I'll connect a LED over here. And a push button over there. And into okay. So when I run this, what will happen is, so you can see a loop. Basically, it is just writing the variable state to the LED pin, right? So it should be off. So when I press this button, uh, I think we should turn off bounds. You just ignore bounds now. So when I press hold this button, the state changes, and you can see the variable state also changes, because whenever I trigger the interrupt, this function will run, because this will pass and it comes here, comes, this will pass and it comes here and changes the state, and then goes back and continue running this. Okay. So when I press the button, it turns the state, toggles the state. So the state will be now on. When I release the button, now again the interrupt gets triggered. This interrupt is getting triggered due to the change. If I set this falling, it will be only triggered whenever I press the button, not release the button. Since we have turned off bounce, we don't have to worry about debouncing. So when I press the button, it will change state. That's the idea. Falling means so from high to low. So by default it will be high. So whenever I press the button, it will be falling. So I press and release, one state change. Again I press and release, another state change. So this function will be getting called whenever I press the button or whenever the interrupt is getting triggered. Right. And this is what we call as ISR, or interrupt service routine. So there is an interrupt that is getting triggered and we need to service that interrupt. And whenever that interrupt is getting serviced, this will run and then it goes back. That's how it works. So now if we were to implement the same thing but using the Atmega IAVR or directly through the registers, what we should do. That's what we are going to see. So first, we'll be having our input statements. So the IO mapping. Main function. So we'll have the global variable state. So basically we just use this thing. Okay. So we'll have the state variable and we'll have this also. This we need a function to change the state, right? Then what do we need? We need to set up these registers. We will set up this first, these things, the pin modes and stuff. How do we do this? LED pin to output. So LED pin is in pin 13, which is PD5. So PD RP setting up 5 to high to set up the output mode. And to set this thing to input pull up, what things we need to do? First we'll set up RT, that is D2, right? So we will explicitly set this up to low. Yeah, I'm resetting that pin, and also I have to do port B. I have to do a pull up part, right? This is basically setting to the input mode, and this is the pull up part. For pull up, we have to set it to 1. So it will be R equal to, this will be port D. Okay. So these two lines we have done. Right? So that is done. Then we have to set these things, this attach interrupt. Let's do this, the loop part. How do we implement the loop? We use a while loop, while one. That is basically the loop. Digital rate of state. So this is the output pin, right? How do we do this digital thing? We have to basically set the port B, this pin, port B. In that we have to set that state. Uh, so now setting the state means state is either 0 or 1, right? So we have to basically set or reset based on the state value. So if state if state we should be setting this bit, else we will be resetting it. Reset and with the negation of it. Basically this is setting, this is resetting. This is this line is basically is right of state. Whatever the state value is, we are writing. If it is a true, we'll be writing this. If it is false, we'll be writing this. Okay. Now we have to attach this interrupt. This line is remaining. Right. To attach this interrupt, we need to look into some registers. So first setting up the falling or this port. So we set for the falling, right? We have to basically set these two bits to uh, 1 0, right? So it will be like assuming by default everything will be 0. You can see the initial value, right? By default everything will be 0. We just need to turn on this one, IIC uh, 1 1. Are we using the one? This one. 2 is 0, 0, right? So 0 in the sense we'll be using IC0, this one. The register will be EICRA in that register. So the register EICRA, which is external interrupt control system A. In that we have to set the value for this one, ISC0 interrupt sense control register 1 1. This 1 1 we have to set, right? Which is IC011. No, it's not 1 1. 0 1, which is around here, the first bit. So the bit value will be 1. Or you can, in this kind of setup, uh, the bit value is not very straightforward, right? In the port registers, the bit values are very straightforward. Everything is 0 to 1. But here the numbers and names are kind of not in very order. So in that sense, you can actually use this ones. If that are not ordered, you can use the bit value of ISC01. That's what we want, right? You can just use the name itself. ISC01 is what we wanted. So that will get the bit value of the. You can see that over here also. That area. See this register, and these values are mapped. So we don't need to remember the bit value. If you know the name of the bit, it's also you will get the number of that particular bit. So we can use it for this kind of registers. We can use it like that. Okay. So for this register, I can just use this. I'm basically turning on that particular value. So this is basically keeping this to falling, setting that to falling. And now what is other register we want? We have to enable that interrupt, right? So with the mask register, we'll be enabling. We need to enable interrupt 0. Interrupt 0 is in BTKD2, right? So interrupt 0 here. So EIMSK, external interrupt mask. In that we'll be enabling external uh, int 0. Int 0 will be enabling. Interrupt 0 will be enabling. So this is enabling the external interrupt. And there are some other things that we need to do to make this like an interrupt service routine. So how to make this an interrupt service routine. So for that, uh, interrupt service routine. Ha. This is how we define the interrupt service routine. So not using the functions to define an ISR, we will be doing this stuff. Define ISR using this ISR uh, thing. You can see this, right? We will be using this wrapper. So this function is there, but we'll be using ISR. Oops, this one like this. Should be like this. ISR. And the interrupt name of that particular interrupt, which is you can see this is the name of that interrupt, right? INT0. That name we'll be using. So it registers that for this particular interrupt. So this is how we define the interrupt service. Let me check. So one more thing that we need to do is to use interrupts. So we've been using this. We need this interrupt.h file also. So we need to include that over here. Interrupt.h. We need that. And also, with this ISR we define using this vectors. Interrupt service vectors. Vector name of the vector that we have to give. So the interrupt service vectors are defined in here also. 328. See, these are the interrupt service vectors. This vector number for each interrupt, there is a number associated with it. And this vector, this is what we want, external interrupt request vector. So given the number, you can use the vector like this. If I see this vector, this is basically another macro which converts the interrupt number. As you can see, there are numbers associated with the interrupt and also the things like that. So here, this is different. So where this macro has been defined. But basically, this is what converts this uh, number, the interrupt number to the interrupt vector. So there might be an address mapping over there, right? And now we need what we need is this interrupt service vector name. Is what we need, and we'll put it here in 0 vect, and this is the function that we need to do the thing. Then also what we need to do is globally enabling the all the interrupts. So to enable the interrupts globally, we use this SEI, like interrupt enable, set interrupt enable bit, which is setting the enabling all the interrupts that will happen. So now we have successfully uh, set up the interrupt thing that we have trying to do. Now let's try running this. So now this should work as expected. When I press this button, one thing, second one, third, fourth. Okay. So basically, we have translated this interrupt-based code into uh, this kind of thing. But now, let's see. Uh, let's see. I This is a challenge for you, like a minimal modification to the same code, right? What I'm going to do is I'll attach another button to this another interrupt thing. So we'll be having two interrupts over here. I'll be connecting this to 3 for another interrupt, and this will be connected to ground. Okay. Oops. Ah. So now our aim is to do this. Uh, Whenever I press this button, it will be on. Whenever I press this button, it will be off. So how to do that? Anyone? Anyone? How will you do that? What are the registers that we need to do? So this is for pin 1. So interrupt 0 is there in this one. Interrupt 1 is here. So whenever I press this button, this need to turn on. Whenever I press this button, it need to turn off. On, off, on, off. We can add a label. Mm, it's a label. So we'll add the label. So visible. Yes. Okay. So now how do we do this? This one? Anyone? So when I trigger this, I need it to be on. So I'll just set to on. When I trigger the other one, which is int one, it's going to be int one, it will be off, right? And then this one, this is for the same thing. We'll copy paste, but for interrupt one, for enabling that for one also. But we can do that in the same line itself, right? We can enable it like this, and we can set up the both things to falling like this, right? The same lane, because those are same registers, right? All those 4 bits are these 2 bits are in the same register, and these 2 bits are in the same register. You can see that, right? uh, you can see the ECR register, all these 4 bits are there. We are using these 2 bits to make it falling, and then uh, this one, these 2 bits are in the same register, so we are using that. Okay, and the state will change based on which interrupt is triggered. So whenever this interrupt triggers, this will be 1. This interrupt triggers, this will be 0. State will be 0. So based on the state of the LED will also change. So now let's see this. So can you tell which one is on and which one is off? This one is on and this one is off. Oops, off is not happening. Uh, 0, 1 and 1, 1. Off is happening. After 3 times it is happening. Okay, this might be due to this one. Byte. So IC11 and IC01 we have changed. IC01, IC11. So it will make both our falling edges. Whenever this is triggered, state should be 0. Seems to be not working every time. Oh, okay. That is because we haven't set up the pull-up thing. So that is not working every time. That's why it should work. This is for the pin 3 also. We have to set up the pull-up mode, right? Otherwise, it will be in the floating state, so that that button press won't be detected every time. So this thing also, what we can do using the same line, setting the both pins to pull up mode. Oops. Now we have set the both pins to this pull up. Now this should work properly. One, off. On, off. Right. Okay. So any doubts in this one? How we are using interrupts?
So can you explain like what does this SPI function do?
I'm not able to hear it properly. Can you repeat? Can you repeat?
Hello.
Ah, yeah, yeah.
Can you explain the SCI function once again
Uh, Sorry, SCA function.
in the interrupt part? Yeah.
SCA,
SEI.
SEI.
Yeah.
This one is like enabling the interrupts globally. So there will be a register. So you can, with one bit, so there are many interrupts, right? You can enable and disable this interrupts globally, like to stop all the interrupts for a certain period of time. To for from triggering any interrupts, you can stop all the interrupts. That will, I think, REI, which is reset enable interrupt. So enable interrupt a particular bit. You can think it of like that. SEI will enable all the interrupts. If I do REI, which will reset that button, so no interrupts will get triggered. You see this? Oops, I think it's not REI. Let me check. Interrupts. Clear, I think. It should be clear. CEI. Uh, Let me check. CEI. Clear. Uh, that. What's the meaning? Uh, just a minute. So it is SCI and CLI. So it's like set interrupt and clear interrupt. So that is available over here itself. You can see this is basically setting a particular value, disable all the interrupts, and this enables all the interrupts globally with a global interrupt mask. It says CI and CLI. So if you use CLI, basically disable all the interrupts, so no interrupt will happen globally. So it's CLI, clear, CL clear, interrupt. SCI means set interrupt. So now
And do you,
no interrupts will happen. All the
okay,
interrupts will, any interrupts will not happen. So to enable it globally, to enable all the interrupts, we use the ACI before going into the main code. So that will enable all the interrupt. So that interrupts will be there. So
okay,
sometimes why that is needed is sometimes you want to do certain task. In between, you don't want them to uh, change the state. Okay, maybe things like that will happen, right? So while doing a particular task, so assume you have a count variable and you are doing some task with that count variable. If a interrupt happens in between and that count variables get changed, so in between that calculation the variable will change, right? So in that cases what we usually do is before doing such operations, we'll clear the interrupts and then do that operation, then enable the interrupt back. So in those cases, that would be useful using CI and CLI. Anything else?
okay, but do
Uh,
we need to like you do the SCI, like isn't it on by default?
I don't think so. Let me check. Uh, because everything will be off usually by default. That's why. Let's just check by not writing it. By default, everything will be off usually, right? Yeah, it's not enabled. So we need to enable it.
Okay, thank you.
Okay. Any other doubts in this one? So you can understand how these pins also work, right? Each pin is connected to a interrupt. And whenever you do this attach interrupt pin number, it correspondingly translate it to the corresponding interrupt vectors and also stuff what we are translating here. Everything these things are actually defined inside the AVR library. Any doubts here? Okay. Then with that we'll stop this session. Thank you. I have shared both the notebooks, right? So sorry, both the project of the things. Here. Thank you.